Welcome to the Explainer, AI that can write poems, debug code, and answer pretty much anything you throw at it. It's suddenly everywhere. But it's not magic. Today, we're going to dig in and really understand how something like a large language model, or LLM, actually works. How does a machine learn? So let's just jump right into the big question, right? It's the one everyone's asking. We throw this word learn around all the time, but what does it really actually mean for a machine? How does a chunk of code go from zero to, well, to writing a sonnet or a Python script? Let's unpack it. To really get it, we've got to rewind the clock all the way back to 1959. A pioneer at IBM, a guy named Arthur Samuel, came up with this definition of machine learning. Now, the magic words here are without being explicitly programmed. Instead of a developer writing a million if this, then that rules, you build a system that figures out the rules all by itself, just by looking at a ton of data. And wow, you can see just how massive that idea became. I mean, for decades, this was a super niche academic thing. But then, boom, something shifted, and the use of the term and the tech itself just exploded. It's become the engine driving so much of the technology we use every single day. Okay, so how does this learning actually happen? Well, it turns out there are really two main roads, two fundamental paths that have gotten us to the kind of AI we see today. The first, and by far the most common, is called supervised learning. Here's a great way to think about it. Back in the day, when Toyota wanted to figure out how to build a better car, what did they do? They went out, bought a Chevrolet, and literally took it apart, piece by piece, to see how all the parts worked together to create the final car. They had the inputs, all the parts, and they had the known output, the finished car. Supervised learning is exactly that. You give the machine tons and tons of examples where you already know the right answer. For instance, let's say we want to predict used car prices. We'd feed the machine a labeled data set, just like this one. You've got your inputs, the car brand, the mileage, the year it was made, and then you have the known output, what it actually sold for. After looking at thousands or even millions of these examples, the machine starts to see the patterns. It learns the relationship between a car's features and its final price. And this is basically what it looks like. After crunching all that data, the model, that little green box in the middle, is now this powerful pattern-recognizing engine. So you can give it the details of a new car, one it's never seen before, and it'll use all those patterns it learned to give you a pretty good prediction of the price. This is the bedrock of so much of what we call AI. All right, so now for the second path. Unsupervised learning. Now this is different. Here, we don't give the machine the answer key. We just hand it a giant, messy pile of data and basically say, go find something interesting. It's pure discovery. The machine is looking for patterns that we, as humans, might not even know exist. Just look at this. On the left, you've got this cloud of raw, unorganized data points. An unsupervised model will go through all of that and start grouping similar things together, creating these clusters you see on the right. This is incredibly powerful for discovering things like hidden customer segments in your user base, or maybe new genres of music, or even spotting brand new types of financial fraud. So let's just boil it all down. Supervised learning is about prediction. You use labeled data because you want to predict a known answer. Unsupervised learning is about discovery. You use unlabeled data to find hidden structures you didn't know were there. Prediction versus discovery. Two different tools for two totally different jobs. Okay, with that foundation in place, let's zoom in on the technology of the moment, large language models, because this is where those basic principles have just kicked off an absolute revolution. You know, it almost sounds too simple to be true, but this really is the secret. For all their mind-bending complexity, models like GPT are, at their heart, just enormous supervised learning systems. They've been trained on a truly staggering amount of text from the internet, and their one and only job is to get ridiculously good at predicting the next word, given all the words that came before it. This quote from Amon's AI journal just nails it. A token is basically a word or a piece of a word. By just learning to predict the next token over and over again across trillions of words, these models build this incredibly rich internal map of grammar, facts, reasoning, and even things like tone and style. It's wild. So this brings us to a huge practical problem, right? The base models know all about the public internet, but what if your company wants to use an LLM to answer questions about its own internal reports or its private customer database? You can't just retrain one of these monster models from scratch. So how do you do it? Well, the answer is this brilliant technique called Retrieval Augmented Generation, or RAG. The best way to think about it is like giving the LLM an open book test. First, all of your private company documents get indexed and stored. Then, when you ask a question, the system instantly finds the most relevant little snippets from your documents. Finally, it bundles your question together with those relevant snippets and hands it all to the LLM, basically saying, hey, answer this question, but only use the information I've just given you. And this brings up a really crucial distinction everyone should know: RAG versus fine-tuning. They sound similar, but they do totally different things. RAG, like we just saw, is for giving the model new knowledge. It's that open book test for facts. Fine-tuning, on the other hand, is about adapting the model's behavior, its style, its tone, its personality. Think of it less like an open book and more like teaching it to speak in a specific dialect or to adopt a certain persona. Use RAG for facts, you use fine-tuning for flair. But as powerful as these models are, the story is nowhere near over. In fact, the bleeding edge of AI research is now running into some really fascinating and kind of tricky new challenges. I mean, you'd think that a model that can write code and explain quantum physics would be a flawless logic machine, right? Well, it turns out they have some pretty surprising blind spots. Take this weird phenomenon that researchers discovered. They call it the reversal curse. So a model gets trained on billions of sentences from the internet, and it sees this fact over and over and over. The capital of France is Paris. It learns that association forwards, no problem. But here's the crazy part. If you then ask the model the reverse question, Paris is the capital of what country? It might completely fail. It learned the information in one direction, but it can't automatically flip it around and infer the reverse. This is a huge clue that these models are incredible pattern matchers, but they don't reason in the same way a human mind does. Not yet, anyway. Another huge challenge is something called the bias-variance trade-off. These targets make it super easy to understand. Bias is about accuracy. Variance is about consistency. So top left, you've got low bias and low variance. You're hitting the bullseye every single time. That's the dream. Top right, you're accurate on average, but your shots are all over the place. That's high variance. Bottom left, you're super consistent, but you're consistently missing the target. That's high bias. And of course, bottom right is the worst of both worlds, inaccurate and inconsistent. Getting that perfect top-left balance is a constant struggle for developers. And this all points to the really big takeaway about where AI is headed. For a while, the race was just about who could build the biggest model. But the focus is really shifting now. The real goal, the holy grail, is to build smarter models. Models that can truly reason, that can generalize from concepts, and can avoid these weird errors like the reversal curse. Which leaves us with one last massive question to think about. These systems are clearly incredible learning machines, and they are getting more powerful every single year. So as we get better and better at teaching them, what's the most important thing we should be teaching them next?